When we talk about vectors, we talk about a one-dimensional way for you to store numbers in, for you to interpret it as a direction as well as a magnitude. But now if we collect all of these vectors and form them into one single object, you call them as matrices, in which this is what we'll be discussing throughout this entire video. So before we get started, please consider liking and subscribing, and also please check the notes in the description for the notes throughout this entire discussion. And alongside with that, I will give you some timestamps for you to skip through, just in case if you want to skip through to a certain part that you really want much more understanding about. So first we'll later discuss about we'll just introduce what is matrices, and then after that we'll be talking about the inverse of the matrix, and then after that we'll be doing the determinant, and finally we'll be doing some transformation of matrices, transformations, and their unique matrices. So these are special matrices. Sorry, so this is not unique, this is special. So here are the timestamps for you to skip through, just in case if you want to refer to it throughout your study. So let's get started by actually introducing what is a matrix. So as we stated at the beginning, if we collect all vectors and form them into one single object, we call them as a matrix. And so a vector is normally written as a column vector, right? So there is M1, M2, and M3, right? And so on, for multidimensional vectors. But maybe you would have some other vectors, which will also have M1, M2, M3, and so on. And so we'll denote this as the component of the first vector, and we'll have the component of the second vector. And this will go on so forth, so you would form something which you call as a matrix. Now for the maximum one, which we'll call as MN, so this is the entry at point M, so it's M going downwards and N going to the sides. We will call this big matrix as an M by N matrix. So what we'll be discussing mostly on this video is when M equals to N, or this is what we call as a square matrix. Square matrix. But we could also discuss about some other type of matrices. So when M equals to 1, or that means that you would have something going like this, M1, 1, M1, 2, and so on. This is what we call as a row vector, because it looks like a vector. But when N is equal to 1, which means that you would go vertically, M1, 1, M2, 1, and so on, this is what we call as a column vector. So what we could see here is that the set of matrix is just a set of row vectors or a set of column vectors that you squish them all together for this entire object to exist. Now, the way that you actually add up a matrix is very similar to how you add up vectors. So if you have M plus N, and this results to Tij, or this is the entry at point I and j, would be Mij plus Nij. This literally means that you added up term by term. So let's say if you have 1, 0, 0, 1, and then you add it up with a 3, 1, 2, 1. What will happen is that you will just sum up each of the terms together. So it's 4, 1, 2, 2. It's as simple as that. Now when you do multiplications, there are two different types of multiplication. We'll first be talking about multiplication with a scalar. So it's A, which is a number, and M, which is a matrix. And so the product will have entries, A, Mij, to be A times Mij. So if we have 1, 0, if we have 3, 1, 2, 1, multiply this by, let's say, 2, this would result in 6, 2, 4, 2. Now lastly, we will be discussing about multiplication by another matrix. So maybe M times X, and we'll denote this as Y. And this might be something that is hard to interpret, but this is the actual definition that I'll be giving you. So So if y and x are column vectors, we'll just assume these guys to be column vectors. We will denote that y is equal to mx is pretty much a way for you to write a system of equation where y1 equals to m11 x1 plus m12 of x2 and so on. And this is similar for y2, which is going to be m21 x1 plus m22 x2 and so on. Same thing for y3, m31 x1 plus m32 x2 and so on. And so if this goes on forever and ever, what we observe is that we could actually denote this as a matrix of the column vector y1, y2, and so on, which is equal to the multiplication of the matrix m, which is m11, m12, m21, m22, and so on. And lastly, we have the vector x1, x2, and x3. So if we observe from this, what we see is that if this guy has, let's say, if this guy has m components, this matrix here should be an m by n, as long as this guy goes to n. So what we see is that m times 1 would be equal to an m times n, multiply that by an n times 1, which means that this will result into an m times 1. So this part actually cancels each other out. And this is pretty much what we'll do in general. So for a matrix multiplication, mn, of let's say m to be an m by n and n to be an n by r, the component of ij would be, so the component of the matrix would be the sum starting from r goes to 1 until n of m ir and n rj. This thing and the top part is the same bit, but written in a different way. And this is the definition of matrix multiplication. So a way that you could actually observe this relation as well is that if you actually have a matrix, let's say let's just do a simple one, which is going to be 1 2 0 1, multiply this by a 3 0 1 0 1 1. And the way that you could actually sum them up is by actually doing something like this. So you first take a row and then you multiply it and you dot product it with the column of the second one. And so this will be at row 1, column 1, which is going to correspond to 3 times 1 plus 2 times 1. And then if you do the same thing, it will be 2. So that and this guy would result to 2. The bottom column goes, the bottom row goes with the bottom column, will be another 1. And the last one would also be a 1. So this would result into the matrix of 5 2 1 1. So there are other types of interpretations that you could take only from these definitions. There are lots of different interpretations that you could take. But here are some properties of matrices. First of all, is that if you take A times B times C, in which all of them are matrices, you could do it as A with B times C, or AB and C. So it is associative. And second of all, is that m times n is not equal to n times m. It's not always. And this is what we call as commutative. So it turns out that matrices are not commutative. And if you are using a square matrix, you could just interpret this in terms of the commutator, m.n, which is defined to be mn subtract that by nm. There is also another type which is called the anti-commutator, which is mn plus nm. It's similar, but we normally use the top definition to define if something is commutative or not, in which this would equal to 0 for commutative. So we have already seen about this interpretation of a system of equation for matrix system, right? And so if you remember from the previous video in which we talked about vector calculus, one of the most prominent thing that we did was actually defining the transformation between one coordinate and the other coordinate. So if you remember, x1 prime is cosine theta of x plus sine of theta of y. And for x2 prime, so if this is x prime and this is y prime, this is gonna be negative sine theta x plus cosine theta y. So we can interpret this into the matrix cosine theta, sine theta, negative sine theta, cosine theta. Multiply this by the xy. And this is what we call as the rotation matrix, or theta, in which this does two different things. If you look at it from an active transformation, in which you transform the vector, what you would see is that your vector spins theta radian counterclockwise, CCW. But if you look at it in a passive transformation, in which you transform your basis, you would see that the axis, so the basis axis, spins theta radian clockwise. So you need to know the difference between an active transformation and a passive transformation, since an active transformation changes the way that a vector works, but a passive transformation transforms the basis for you to describe such vector. And both of them are very useful for you to remember when you're doing transformation of variables, or maybe even some transformation of the, let's say, position. So if we look at this in terms of transformation, let's say y equals to m times n times x, what we see here, so let's say if these are vectors, what we need to view is that you could actually state that this entire object to be the total transformation, right? And how do you interpret this total transformation? So you first do a transformation of x with n first. So this will transform it into something else. And then you will transform the entire thing in terms of m. So the way that it is ordered is that you transform it by n first, and then you transform it by m. And so if you look at the commutator, it is different as if you're doing m first and then n. There are lots of examples. Let's say reflection. If you reflect first within this angle, and then you reflect it within this one, it would result in a different position. Compare that if you transform, let's say, your point across first and then through the y-axis. This is a visual interpretation that you could take thanks to the idea of transformation. So remember when we talked about the unit vector as well as the zero vector? It turns out that for matrices we have also these kinds of objects. So we have the zero matrix, in which everything ij is always equal to 0. So this is the matrix 0 is the matrix where everything is 0. And the other one is a unit, it's the identity matrix. Identity matrix, in which your component in ii is always 1, and ij is equal to 0 as long as I is not equal to j. So it is like ones within the diagonal, but 0 everywhere else. And these two matrices are pretty cool, because if you take the sum of a matrix with the 0, it is obvious that you would get the m. And same thing for the identity matrix. If you multiply I times m, it will be m. Same thing with m times I, which is also equal to m, which means that the identity matrix commutes with almost every single type of matrix. So something interesting to talk about matrices is that if you know that a matrix m times n is equal to 0, it doesn't mean that m is 0 or n is 0. It doesn't imply something like that, but the reverse is true, not the one going forward. And so this could also conclude that m squared equal to 0 doesn't truly mean that m equals to 0. There are lots of examples of this. One of them is if you take 1, 0, 0, 0, no, sorry, yeah, 1, 0, 0, 0, and 0, 0, 0, 1, and then you take the dot, what you would get is the 0 matrix. So that's everything for you to know about matrices in general. But we could actually define a very interesting type of matrix, which we call as the inverse. So the inverse works like a reciprocal, or the conjugate, but it much more works like a reciprocal. So something like a times 1 over a is equal to 1. Same thing for matrices. M times the M inverse is equal to the identity matrix. And it turns out that this also commutes with itself. So it's M inverse times M is the same thing as the identity. So this matrix here is something which we call as the inverse. So it's something that, so it is a family of, so it is a transformation of the matrix M which results it into the identity matrix. And we can do this for the 2 by 2. So the M inverse for a 2 by 2 is defined to be the determinant of, so the reciprocal of the determinant of M with the terms M22, negative M12, negative M21, and M11. So the determinant here is defined to be M11, M22 minus M12, M21. Now, thanks to this idea of the inverse, you could actually solve a system of equation. It's literally that useful. So if we have y equals to mx, in which this is a system of equation, and let's say y is already known, and we want to find what is x. The way that you could do this is that you could multiply both sides by the m inverse, as long as it exists. And so why did I say that the m inverse must exist for this thing to happen? Well, it is because if the determinant is 0, it would mean that you would have a unique solution. There will be lots of solutions that solve this problem. So in here we'll be assuming that your determinant of m would not equal to 0. But when it is equal to 0, the inverse doesn't exist. So continue on. If we know this vector and we know the m inverse, we could determine what is the x. And this is very useful to do, especially when you're doing computer science, is that you normally play with matrices instead of using system of equations every single time. Because computers are very good at handling matrices. And one of the most prominent type of programming language for engineering is MATLAB. And MATLAB uses matrices a lot in terms of doing its computation, figuring out eigenvalues, and much more. But all of those technical stuff within linear algebra won't be discussed here. So if you want some discussion within linear algebra, please share it in the comment section below for me to discuss in a much more fuller detail. So anyways, let's go back to the idea of the inverse now. Let's say if you take the multiplication of m times n, and we take the inverse. This multiplied by mn must equal to the identity, and we want to figure out what is the mn inverse. So we could multiply both. So if we know that n inverse is the same thing as n inverse, we could just multiply this entire thing straight away. Mn inverse of mn. And now this combines into the identity matrix. And so if you do the same thing, what you would get is mn inverse to be the same thing as n inverse m inverse. So it turns out that you flipped the way for you to compute the multiplication. So instead of doing m times n, then doing everything inversed, you could just find the inverse of m, the inverse of n multiplied by the inverse of m. So what we have discussed fully in here is the idea of the inverse within 2 dimensions, within a 2 by 2 matrix, sorry. But what about for 3 dimensions? So this is the idea of determinants comes in, as well as the cofactor. But before we go into that, we want to figure out what are properties of determinants. So if we only observe from the first part here, there are multiple properties that we could gain. The first is that the determinant of m n must be equal to the determinant of m and the determinant of n. This is something that I won't prove, but you could actually observe this if you do the 2 by 2 matrix computation. Another thing is that if you take the m transpose, or this is basically, so m transpose in terms of ij is the same thing as mji. So you pretty much flip your matrix around. So it will be something like this: 1, 1, 2, 0. Okay? And it turns out that the determinant of this m transpose is the same thing as the m. The third thing is that if you take MA, so what is MA? MA is multiply one row or column by A. It turns out that it will be A to the determinant of M. And so another one is if you do an M exchange, or if you flip one row or column with another, this would equal to the negative of the determinant of M. Now, something that I want to extend further is the Mn here. So if we take the M and M inverse, it becomes M and M inverse. The determinant of M multiplied by the determinant of M inverse. And this must equal to the determinant of I, right? Which is actually 1. We could just compute this straight away. And so it turns out that the M inverse is just 1 over the determinant of M. So now with this, we could try to develop the idea for the determinant, not only for a 3 by 3, but also for bigger matrices. So the way that we'll define that is by first defining a cofactor. So the cofactor of the matrix M will have entries ij to be -1, I plus j, and I point j of the matrix M, the determinant of I point j of M. And so what does this mean? So let's just do an example. Let's do A, B, C, D, E, F, G, H, I. We'll just take this 3 by 3 matrix and we'll just do the cofactor. So first, we'll just define what is the cofactor within the first term, the 1, 1. So at the 1, 1 here, it would have -1 to the power of 1 plus 1, which is 2, so it's going to be +1. So it's going to be a positive sign. And then you take the determinant of I point j of M. And so this actually means that you remove row I, column j. Yeah, you just need to remove row I and column j. So remove column I, 1, remove row 1, column 1, and then you take the determinant of E, F, H, I. So it's just so it will be EI minus FH. And so for row 1, column 2, it's going to be a negative sign because negative 1 to the power 3. And then if you delete these guys, what you would get is the determinant of, let's see. Yep. So it will be the determinant of di minus fg. And if you do this so on, what you would get is the cofactor. So why is the cofactor important? And this will later define what is the determinant. So the determinant is defined to be the sum of j equals to 1 until the n by n. So this only works for square matrices anyways. It's going to be j equals to 1 until n of m1j and mc 1j. So what does this mean? So you just take the component of the first part. So let's actually do another part here, just to make it complete. dh minus ge. There we go. So what this means is that you would take the m in terms of the 1j. So starting from 1, m11 is a. Multiply this by the mc of 1j, which is ei minus fh, and then you add it with b, which is m12, and negative. So it's fg minus di, and then lastly you have c of dh minus ge, and so on for n by n. And this is the determinant. And it turns out that you could actually flip up almost all of the signs. No, sorry, you could just swap out all of your matrices thanks to the idea of the properties. And it turns out that this one here is actually just arbitrary. You could just choose it to be 2 or 3, or even you could just change the 1 into an I, and then you turn the j into a value. It also works as long as it is within the same row and the same column. And that's the definition of the determinant. So we can define what is the definition of the inverse, which is going to be the cofactor transposed over the determinant. So something that you should also look at this is that it looks like as if we are doing a cross product, which we are actually doing. So if we take A cross B, what we observe is it is something like ijk of ax ay az and bx by bz. It is as if we are taking the determinant of this thing, even though that we are doing the determinant with a vector. And it's fine. It's just a formality for you to write the cross product. Same thing with curl. If you take the curl of A, it's going to be ijk of partial over partial x, partial over partial y, and partial over partial z of ax, ay, az. And so also, because we know about the triple product, sorry, so this is this is the determinant. Also for the triple product, if we combine it with this guy, we end up getting we end up getting just a determinant of all of the vectors together, something like this: by bz, cx cy cz. It's a very interesting observation that we did. Also, you could also do the Jacobian. So the way that we could actually define the Jacobian for xyz over uvw is just going to be the cross product of all of the scaling factors, which it turns out to be dx over du, partial y over partial u, partial z over partial u, partial x over partial v, partial y over partial v, partial z over partial v, partial x over partial w, partial y over partial w, and partial z over partial w. You just take this determinant and you would get the Jacobian. And this is very interesting because Previously, we have only been doing conversion of coordinates in terms of another orthogonal coordinate system. And in here, we end up using any type of system as long as it is independent with each other to get the Jacobian for you to use for your integrals, which is very interesting. So let's take the idea of this guy to be the matrix M. And we could actually define an M inverse, which is going to be corresponding to column vectors of A reciprocal, B reciprocal, and C reciprocal in the column. So it's like that. A Z star, a B star, B star, C star, C star, and this is XYZ, XYZ. There we go. So if we define two vectors like this, and then we do M dot M inverse, what we could see is that we are actually forming A dot A star is going to correspond to 1, and then A dot B star, and etc. corresponds to 0. Now, with this, we could define the reciprocal vector. And so this observation from the properties of the inverse tells us that A star must be perpendicular to both B and C, which means B cross C is a viable option. And then you would just divide this by the length of B cross C. And then we'll just compare A as well as the A star. And so if we take the determinant here, the determinant of A must be also with the determinant of 1 over A was to equal to 1, right? So this means that this must be multiplied again by the determinant of A here. So it turns out that this becomes B cross C over M. And this is what we call as the reciprocal vector. So the reciprocal vector is very important, especially for material science, because we are doing crystallography, in which we use the reciprocal vector to describe planes. So I won't fully discuss about planes here, but if you want more discussion about crystallography, you could just leave it also in the comments. So sorry, this should be the determinant, my bad. Finally, we can talk about some transformations. So some transformations that we have already introduced include the transpose, M transpose, right? And so there's also another type of transformation that I want to introduce, which is the dagger. And what is the dagger? The M dagger is something which we call as the adjoint. So the adjoint is defined to be the conjugate of the matrix. You take the transpose. So this means that your matrix here could be complex. And this is exactly what we are hoping. If we are doing a real one, it will transform into an M transpose if this is real. But if it is complex, we take the dagger, it becomes something like this. And with only these two types of transformations, we have some unique matrices that I'll be describing here. The first is that when M equals to M transpose, this is something which we call as a symmetric matrix. And so if M equals to negative M transpose, we call this as anti-symmetric. And so we could do the same thing for daggers. M equals to M dagger corresponds to something which we call as the Hermitian. If we have it to be equal to negative M dagger, we call this as anti-Hermitian. Now, let's think of another case. What if we multiply M and M transpose, and we got the identity? This means that M transpose is your M inverse. So we could have another relation, M inverse equals to M transpose. We call this as a orthogonal matrix. And this only works for real matrices. But if we think of M times M dagger equals to the identity, we call this as the unitary matrix. So it turns out that if your matrix is real, it becomes into an a unitary matrix is a orthogonal matrix. So these matrices are pretty important, and normally and you would sometimes use it for you to describe a system, or maybe even when you do quantum mechanics, in which the Hermitian comes into play. But I won't fully describe about the uses in here. This is just an introduction of matrices. You could also do operations with matrices. Something like m squared corresponds to m times m to the power of n would literally corresponds to m times m, n times, and so on. You could also do a power, the exponential of m, which is already defined from the Taylor series to be m to the power of n over n factorial. But this is something that I want you to keep in mind. You could do e to the power of theta L and e to the power of phi L, and it supplies you with e to the power of theta plus phi L. This is given as long as theta and phi are scalars. But if you do e theta L and e phi m, what you would get is not e theta L plus phi m. Instead, you would have another commutator here. Multiply that by the phi over 2. Theta phi over 2. And this is the main, and this is why. If we state that theta L and theta m and phi m to be matrices, because as we know, the result must be the same matrix, these two must commute with each other for it to form e theta L plus e phi m. Otherwise, if you flip it around, it would have a different value. So this is why we have the commutator here, for us to describe the flipping. You could also prove this by expansion of the Taylor series, and it literally forms into this type of relation. So mostly when we discuss about matrices is that we describe it as a column vector, multiply that by a transformation, and your column vector again. But let's say if you think of the transpose. So instead, what you're talking about now is two row vectors. And so this supplies you with a pretty cool information. Same thing with daggers. It turns out daggers also have a similar property with transposes, is that you would just flip the coordinate system around. And so with this, you actually transform your order of transformation from left to right. From left to right. So if, let's say, y transpose equals to x transpose mn, you do m first and then n. Also, from this type of transformation, what we could see is that you could actually express any type of matrix to be first this m plus m dagger over 2, which if you think of it very much, this is Hermitian, and m minus m dagger over 2, and this is anti-Hermitian. And you could actually transform this guy into I times m minus m dagger over 2i. And it turns out that this thing here is Hermitian. So it's a pretty useful information, especially when you're doing, let's say, the multiplication, is that if you actually separate them out, you could just get a Hermitian as well as a anti-Hermitian. Lastly, that I want to describe about matrices is that you would have something which you call as the trace. So the trace of a n by n matrix is defined to be just the sum from I equals to 1 until n of mii. So you're just summing up all of the values of the diagonal. So here are some properties of the trace. The trace of m times n is the same thing as the trace of m. And the way that you could see this is by literally expanding it, and you would see that if you regroup it in a certain way, you'd get the trace of nm instead of the trace of mn. It's just a matter of the regrouping. So with all of these informations, you have already known much about matrices and also the determinants, especially when you're doing physics. So there are lots of uses of matrices. One of them is solving systems of equations, but there are also other types of usages, like solving a system of differential equations, or doing quantum mechanics, in which you instead take the angular momentum to be a operator in terms of a matrix, and so on and so forth. So I won't fully discuss about the usage of matrices here, but we'll later be visiting them again when we talk about much more advanced physics. And so that's all for today's video when we talked about matrices. So thank you very much for watching. Make sure to like and subscribe. And also please share this to your friends who really needs to understand physics in a much more deeper understanding. This is Understanding Physics, and I will see you on the next video.